All right, wrapping up section 4.3 brings us to Bayes' theorem. So Bayes' theorem deals with conditional probability. And as I may have mentioned last time, there is a sort of scary looking formula for Bayes' theorem, which we are not going to bother with. Okay. So here's a good Bayes' theorem example, another uplifting example. Suppose cancer has a 1% prevalence rate. I don't think it's actually that high, meaning that 1% of the population has cancer. Denoting the event of having cancer by C, we have the probability of C as 0.01 for a subject randomly selected from the population. Okay. So far they haven't asked me a question. This result is included with the following performance characteristics of a test for cancer. All right, so this is what they already told me. The probability that a randomly chosen person has cancer is 0.01. The false positive rate is 10%, which means the probability of getting a positive result given that cancer is not present is 0.1. That seems kind of high. And the true positive rate is 80%, which means the probability of a positive result given the cancer is present is 0.8. All right, so they want me to find the probability that cancer is present given that the test result is positive. Okay. All right, so the way that we're going to do this, and again, there is this sort of complicated, scary looking formula, which I really don't want to bother with. The way that we're going to do this is we're going to cook up a fictional, I'm going to call it a sample of 1,000 people, and we're going to categorize those 1,000 people based on these probabilities that they've given me. Okay, so that looks like this. So here's my 1,000 people. So to start off with, we know that 1% of the population has cancer. So that's these 10 people right here. 10 people out of 1,000 is 1%. Okay. And then we know that out of those 10 people, the test will detect cancer in 8 of them, because 8 out of 10 is 80%. And, okay, which means that the other 2 people, it won't detect the cancer. Okay, so let me bring up my pen here so that I can try to be clear on, you know, what numbers are coming from where. So the first, if you were watching me fill in this chart, I would put this 10 first. That's 1% of the whole population of 1,000 people. The next number I would put would be the 8. So that's 80% of the 10. Okay. So I would put this first, I would put this second, and then I would put this third. This is just from 10 minus 8 equals 2. Okay. All right. The next thing we have is that the false positive rate is 10%, okay? So we know that 10 people have cancer, which means 990 people don't, right? So I guess I could have put this number in, you know, as soon as I put the 10 there. But this 99 right here, this is 10% of 990. That's where that came from, 10% of 990. Okay. All right, so it's kind of like doing a puzzle. You know, they give you the numbers and you just fill out the things that you know based on what they told you, and then you kind of use subtraction to fill in the rest. Okay, actually these next few slides just kind of explain the same things that you just saw me try to explain using my pen and the scribbles. I think it would be worth looking at this. We'll look at it kind of quick since we've already done it. So they're highlighting the cells I guess the idea is they're highlighting them as they figure them out. So the first thing they figured out is the 10. 10 is 1% of 1,000. Okay. The next thing they figured out was that must mean the other 990 people don't have cancer. Okay. Then they went over to the 99. They said 10% of 990 is 99. Okay. So this test is going to say that 99 of these people have cancer even though they don't. Okay. That's called a false positive. And that means that the remaining 891 people who don't have cancer, the test is going to say they don't have cancer. Okay. Then we go back up to the 10 people. The test is going to detect cancer in 80% of them. So that's 8 people out of 10, which means it will not detect cancer in the other 2 people. Okay. All right, so the question was, find the probability that the person has cancer given that they tested positive. So we talked about 2 different ways to do conditional probability. You can use what's called the intuitive approach, which if your data is organized in a table is usually easier. Okay? Otherwise, you can use the formula that we talked about. So let's use the intuitive approach for this. To find the probability that the person has cancer given that they tested positive, we're going to reduce our sample space down to only the people who tested positive, which are these people right here. So that is my whole entire sample space. Okay. So given that we're talking about one of these people, what is the probability that when I pick a person out of this group, they actually have cancer? Well, there's 107 people who tested positive. Only 8 of those people actually have cancer. Okay? So if you lived in this population and you went to the doctor and they gave you a cancer test and it tested positive, there's still only about a 7.5% chance that you actually have cancer. So the moral of the story is you either need tests that are much more reliable, okay, or you need to, if you get a positive result, you should do the test again, okay, or even both of those things. Okay. All right. So it's kind of surprising, right? You know, you take this test, it says you have cancer, there's actually only a 7.5% chance that you actually do. But 80% or let's see, 20% false negative rate and a 10% false positive rate, that's kind of high, all right? So not a very good test. All right. And I think that's basically what it says on this last slide. For the data given in this example, a randomly selected subject has a 1% chance of cancer. But if you take a test and it comes up positive, the chance of cancer increases to 7.5%. Based on the data given in the example, a positive test result should not be devastating news because there's still a good chance that the test is wrong. Okay. All right, that brings us to the end of 4.3. Your author does love his vocabulary. All right, so this is another vocabulary term that I don't remember seeing in any other book. He likes to distinguish between prior and posterior probability. So let's talk about what that means. A prior probability is an initial probability value originally obtained before any additional information is obtained. So an example of that in the problem we just did would be 1% of the population has cancer. That is a prior probability, not taking into account any other information. Okay. As opposed to a posterior probability, that's a probability value that has been revised by using additional information. So an example of that would be the probability that you have cancer given that you tested positive is 0.0748. That's an example of a posterior probability. It uses additional information. So conditional probabilities are often this second kind, posterior probability, because it takes into account additional information. All right. And so this is what you just heard me say. The probability, or 1% of the population has cancer, that's a prior probability. Probability person has cancer given that they tested positive, that's a posterior probability.